Let's return now back to Niels Bohr and the guesswork that he did. So, if we go back into history, and I'm not a big history buff, but if we go back into history, Bohr was working with Rutherford on atomic physics. But Niels Bohr really felt that Max Planck and Einstein were onto some really, really good ideas. Bohr really felt that if light is to be emitted at a specific frequency, then what we've known of having this HF to be that energy of a photon, that's going to be the energy of the upper minus the energy of the lower, which is really, once again, what we're just talking about here is, you know, if we have our energy levels, like here's the ground level, here's 1, we've got to go from 2 to 1, and when we do that, we'll emit a photon. Okay, that's all it's talking about there. So the energy of a photon emitted, HF, or as we have been writing in this class, H nu, if you want to write it like that, doesn't matter, have fun. That's just the energy difference from the upper and lower energy levels. Okay? Now, Niels Bohr, he predicted that these electrons are moving in orbits. Okay? Which we've already talked about in a prior video that this idea is wrong. Like, we don't have a positive nucleus here, and then we have the electrons going around in these nice circular orbits. That's not a thing. But, at this point in time, that's what Bohr thought. Or rather, that's what he predicted. Okay? Like I said, we know this isn't true, but this is what Bohr thought. And it's a not bad idea. However, because of this idea, Bohr had another thought. If these particles, if these electrons out here are moving in a circular orbital path, they're not, but let's pretend they are. If they are, then just like the planets, these suckers have an angular momentum. It's a mass moving in a circular orbit. So we can say that angular momentum equals a moment of inertia multiplied by some angular velocity, which is exactly what my intro students are learning about right now. Now, if we do this for a point charge, which is what we'd consider an electron, the moment of inertia would be mr squared, and then converting this angular velocity into a linear velocity, we'd get v over r. Which, as we see, this is the exact same moment of inertia we have for our planets, or the angular momentum for the planets is just going to be mrv. And technically speaking, for all of you hyper mathematicians out there, technically this r and v are vectors, and this is a cross product, like that. But we're not really going to concern ourselves with it, because in reality, that's just a right-hand rule. Flashbacks to right-hand rules. But really, we can just think of it as MRV, okay? We don't have to go any further. Now, with this idea, which the actual idea behind electrons orbiting in this way is wrong, and resume. Okay, so with this, a little bit of fun math was done. And with this little bit of fun math, somehow we are going to show that the angular momentum of a electron orbiting around the nucleus is equal to mrnv, where this is the radius of the orbit at a specific energy level, right? Because I could be at like lower energy levels, or I could be at higher energy levels, so that's a specific energy level there. And this is equal to n, what energy level are we at, what principal quantum number, h over 2 pi. And as we briefly mentioned earlier, this h over 2 pi comes up so often that we can actually just call this n h bar. Once again, where n is your principal quantum number, what energy level is that electron at? So how do we actually do this fun math, and where do we get this nonsense from? Because we already know Niels Bohr is wrong, but this is right. So let's see just what happened here in a rather lengthy derivation. So loosen up. We're going to be diving in. Let's first just redraw this like bad idea of an atom. We're going to have here in the center some positive nucleus. Let's say this positive nucleus is going to have some z number of positive charges. So like some z number of protons. And each positive charge, we remember, is equal to an elementary charge E. So this is some number of elementary charges in the nucleus. We're then going to have an electron out here that is making this orbital path. Once again, I cannot stress this enough. This is not what actually happens, but we're just going to roll with it. Because of this, one of the first things we learned in this class, that positive and negative charges are attracted to one another. This is Coulomb's law. If we use Coulomb's law, we can say here that F equals, well, this is going to be K QQ over R squared. Well, one of our Q's here is Z times the elementary charge. The other Q we're going to have is an elementary charge, because that's what an electron is. It has the elementary charge. And then divided by R squared, the distance between them. Recall, I'm kind of ignoring sign conventions here of like positive and negative because I know these are going to be attracted to one another, so who really cares? But I can quickly just rewrite this as KZ E squared over R squared. Now, if you recall, for circular motion, F, well, it also equals, just in general, ma. And for circular motion, that's a centripetal acceleration, which means that we can say this is equal to m v squared over r, because v squared over r is a centripetal acceleration. Well, what does this do for us? Let's now solve this for r. What is the radius at some position? We're going to drop an r out, multiply by an r, divide by an mv squared. And what we're going to have is r at some principal quantum number is going to be equal to kz e squared over the mass multiplied by v squared. And note, this is like a nice mass of an electron here because that's what we've been talking about as the orbiting particle. Okay, so we could actually write this as me if we want. We'll just kind of ignore it because it is the mass of the electron. Okay? Now, let's just do a little bit of fun math. Recall what we just wrote about angular momentum a moment ago. We said L equals mRV. And we also said, just kind of like waving our hands around, that that's equal to NH bar. What this means is that we can solve for V. V equals NH bar over MR. And we're going to take this quantity and we're going to substitute it in for the V. So what we now can get is the following. We can say Rn is equal to Kz E squared divided by M times the quantity of, and then this is going to be NH bar over MR squared and then if we square all the terms on the inside and then reduce this to make it look a little nicer, we're going to get KZE squared times a mass times Rn squared, because this came from the bottom up to the numerator, and then divided by n squared h bar squared. Which means, now that I've got an Rn equal to some Rn squareds, one of them's going to go away, and then I'm going to have to transfer all the terms over to the other side. So dropping one of the r's out, and then basically playing a reciprocal game or a cross multiplication, we are going to get that Rn is equal to n squared h bar squared over k z e squared m. Whew. Which we are then going to simply call this n squared over z multiplied by R1. What the heck is that R1? Well, h bar squared is a constant. K, Coulomb's constant, is a constant. E is the elementary charge, which is a constant. And this m is the mass of an electron, which is constant. If I take all these constants and put them together, they are going to equal R1. So R1 here is equal to h bar squared over mke squared. In short, R1 is equal to 0.529 times 10th to the minus 10th meters. We call this the Bohr radius. This is the radius that an electron will orbit at the lowest principal quantum number. Okay, so it's like the lowest radius of an electron's orbit, which isn't really a thing, but it's how we think of it. And that is simply setting n equal to 1. 1 squared is 1, so we just get R1 over Z. Okay? Now recall, this Z quantity here was the number of positive charges in our nucleus. So, if we set Z equal to just 1 here for hydrogen, which is literally made up of just a proton and an electron, if Z equal 1 for hydrogen, then all we see here is that Rn equals n squared times R1 for hydrogen. That is Z equals 1. If for some reason we don't have hydrogen, we've got helium, then that Z is going to equal 2, and we're going to have to go back up into this equation and use it up there. Okay, but Rn equals n squared times R1 is a nice thing for spectral hydrogen. Now, like I said, if we didn't have hydrogen, this equation would change just ever so slightly. We just put that Z back in. We just get n squared over Z times R1. Nothing crazy there. Okay? Well, remember, n, which is drawn very poorly here, or written very poorly, this n is just the principal quantum number. What energy level is that electron at within this orbit, which isn't really a thing. Okay? And like I say, the orbits are not actual orbits. It's just how we think about it. There is not a defined path that the electrons are going around. It just happens to work out here. Okay? Now, why is this so nice to think about? Now, this idea of the orbit is really, really helpful here because in an orbit, we can have some energy. We can define an energy amount. For instance, recall that our total mechanical energy of a system is just the idea of a kinetic energy plus some potential energy. We can think of the potential energy here as being the negative of the charge and a voltage. Remember, if you put a charge through a voltage, you get a potential energy. Remember, a voltage, also just called a potential, a charge in that potential has some potential energy. So, while this would just read QV, our Q here is the elementary charge. So there's E. And then for a voltage, there's V. This is not an electron volt. Well, it can be an electron volt because one electron put through 1 volt is the definition of the electron volt. But we see it's a charge through a voltage. It just so happens that this we can define using Coulomb's law and the ideas from electrostatics as well. We know this would be negative kZe squared over R. This is kQq over R. And we have defined our potential as being negative. If we want that total energy then, what is the energy at some position? Well, we know it's going to be a 1/2 mv squared because that's kinetic energy. And then plus our negative kZe squared over R. That is our total energy. Where this R is really Rn. It's the radius at some level. Now, what can we do with that? Well, we can do with this what we've kind of already done. We know we can rewrite velocity due to angular momentum as nh bar over Rn times m. And we can take that quantity and drop it in here. We also know that we can rewrite Rn as being equal to the n squared over z times R1, which we're going to write it out in completeness. That is the n squared h bar squared over mkz, isn't that a type of Lincoln? E squared. And we're going to shove this right into here. So now, with our substitutions, we're going to get the following. There is math that is done right here. There are some algebra steps. We combine terms. We make our denominators nice so we can subtract it all together. In the end, what we are left with is the energy at some level is equal to negative z squared e to the 4th m k squared over 2h bar squared multiplied by 1 over n squared. Now, why did I write that in a slightly weird way? Well, z, e, m, k, and h bar, and the number 2, these are all constants. So they all just, they go together. It turns out that if you put all of these constants together, and then you convert them into electron volts, you get exactly negative 13.6 eV. Now, this Z here, that's a value of 1 for spectral hydrogen. If we have helium, lithium, etc., that Z value can change. Which means this 13.6 is going to be amended by Z squared over N squared. This gives us an energy level of any possible substance, or possible element, should I say, at some sort of energy level. This equation we have here, this En equals negative 13.6 electron volts times Z squared over N squared, where Z is the number of protons in the nucleus and N is the level you are at. It's that principal quantum number. This is the equation we use to build our electron energy level diagrams. So those diagrams where we had a hypothetical atom, it was like 6, 3, 1, and then 0, we use this equation to build these for actual things. So for something like hydrogen at energy level 1 in the denominator, this would be negative 13.6 down here. As we move up to our first excited state, our second level, that'd be like 13.6 divided by 2 squared, which is 4. This would have a value of negative 3.4. When we go up and up, our next level would be like negative 1.511111, repeating. 13.6 divided by 16.85. And because we're dividing this by n squared, which just vanished, because we're dividing that by n squared, which just came back, fight you game. What's going to happen is over time, these are actually going to get closer and closer and closer together, okay? And if you want to completely escape out of a hydrogen atom, if that electron wants to completely escape from the hydrogen, you need a total of 13.6 electron volts to get out. That will take you from here all the way out to the 0 position, because that 0 position is negative 13.6 divided by infinity squared, which is kind of a weird thing to think about. It's effectively 0, which just means 13.6 is the ionization energy for hydrogen. If we did this for helium, very similar, but down here we'd have to have 13.6 times 2 squared, so that's 4. So our base level for helium would be negative 54.4. And then we'd start working our way up like that. As you get heavier and heavier elements, it gets harder for that electron to escape. There's more of a Coulomb's law of an attraction pulling it in at those base levels, and there's some shielding properties that are happening as well. But this is where our electron energy level diagrams are coming from. It is this equation. This equation is super duper important. Get rid of that other square. This is very, very important. You should get that one like tattooed on your eyelid. Don't do that. That'd be weird. But if you did, you would not get any bonus. Nate just asked if we could get bonus. Good effort, Nate. Now here's a wild one. This is where things get really bizarre. Up here, we had this wild set of constants, right? Some z squared, which is just how many protons do you have, and then a bunch of constants to give us that 13.6. I'm going to go back to this idea. In our last video, we talked about line emission for absorption and emission lines and a Rydberg equation, which Balmer used to find Balmer lines and Paschen used for Paschen lines and Lyman for Lyman lines. So using the Rydberg equation, we've got 1 over lambda. That's how it starts. But let's think about what 1 over lambda actually is. Well, if we think about the speed of light, we can think of this as actually being Planck's constant multiplied by a frequency divided by Planck's constant in the speed of light. Now, yes, I realize that Planck's constants divide out here, but I'm going to leave them. And I also realize this is really just a rewrite of the speed of light equation. C equals lambda times the frequency. But if I do this, I will recognize that h nu, well, that's Planck's constant multiplied by a frequency. That's the energy of a photon. Well, I can rewrite the energy of a photon as being 1 over hc, because that's in the denominator. And the energy of the photon is En minus En, where we have some like final and initial position, right? Our upper minus the lower. This is like the upper location. This is like our lower location. It's just the difference in those energies, okay? So with this now, I'm going to expand this into a giant thing. 1 over lambda equals, I can state that this is going to be positive because I know that this difference in energy here is going to be a positive. When I do my final minus initial, I'm going to have, or my upper minus the lowers, I'm going to get positive quantities out of here for energy. That's why I have the photon of light. And then I'm going to get z squared e to the 4th m k squared over 2h bar over hc times 1 over n squared minus 1 over n squared. It turns out if you put all of this together, we already know what that will equal. This is R. It's the Rydberg constant. It is equal to 1.1 times 10 to the 7th inverse meters. How wild and wacky is that? And this does continue the assumption, as Mikey's just pointed out, that this equals 1.1 times 10 to the 7th when Z is 1 for hydrogen, okay? If we didn't have hydrogen, this would have to be like RZ squared and then times the quantity. Now, that Rydberg equation that we originally had from the emission spectra, that was originally found just by fitting. It was just found by graphing things and then finding a slope. Now, we have analytically proven that all of these constants together give us that value back. And the totally wild thing about this is that when Bohr did this, Bohr said that MVRN or MRNV equals NH bar. We know this idea now is bogus. The electrons are not moving around in these predefined orbits, which means that this entire idea was guesswork. It was educated guesswork. We had a hunch. The underlying baseline assumptions about how we got that hunch were wrong, but this hunch was correct. And simply by following a good hunch and a good guess, we were able to analytically prove this equation. And sometimes that's what physics is. You're following a hunch. You're following some ideas. You've done something previously that might look the same, and you're seeing where it takes you. And until something else comes along and says, this is wrong, like we later learn about electron orbital clouds and that Bohr is wrong, well, we take it for what it is. Okay? So, kind of a neat thing. Goes back and reproves the Balmer equation via, or the Rydberg equation, which Balmer and Paschen and Lyman used, via these orbits, even though those orbits didn't exactly exist. This finishes out for us the world of modern physics, but not all of it. What we're going to work into next in our next videos is nuclear physics. This is still in the world of modern, but it starts getting away from our ideas of light, and it starts looking into some other things that came about at the turn of the century. So until next time, adios, and take it easy.